G'day folks, in this pre-lab video we're going to have a look at some of the background behind your experiment, which is focusing on quantification of pollutants in some water samples that we've actually taken from an authentic site in Queensland. In fact, these samples have been sent down to us so that we could do some testing. The water comes from a regional lake which has been polluted by a river which has some water in it from a dam which has overflowed. Unfortunately, that dam was capturing a lot of the waste from a mine which was upstream. It was a copper mine, but there are other sorts of pollutants in there as well. So you're going to be measuring the concentration of these heavy metal pollutants, and we're going to be using spectrophotometry. In this experiment, you'll be performing both a qualitative and a quantitative analysis. In case you're not sure what I mean, in simple terms, it is what is in the solution and how much. In other words, what's the concentration of those pollutants. Inorganic salts often exhibit colour, and it's the fact that they exhibit colour that we're able to use spectrophotometry to measure the concentration. As you're probably aware, when most materials exhibit colour, it's because they're absorbing light in the visible region. What's more, we know that the observed colour corresponds to the complementary colour that is actually being absorbed. So for example, we can use a colour wheel like this. If we see that something has a green colour, we look to the colour on the opposite side of the colour wheel. In this case, it would be so-called red-violet, and that would be representative of the colour that's actually being absorbed by the material. In inorganic salts, the colour that we observe is usually due to D electronic transitions. It requires an incomplete D subshell. So this obviously corresponds to most of the transition metals in the periodic table. This is what we call crystal field theory, and it's really Chem 1052 content, so we won't talk too much about that now. More importantly, we can exploit this absorbance of visible light to quantify the concentration of a solution. And so in today's experiment, you're going to take polluted water from this regional lake using an authentic sample that's been sent to us. To do a quantitative analysis using spectrophotometry, we ultimately have to set up a calibration curve. So a calibration curve is basically a graph which graphs the absorbance of visible light by the solution with respect to the concentration. So we set up our calibration curve by measuring the absorbance of a series of standards. In other words, in this case we have 4 standards and they have a known concentration. We use our spectrophotometer to measure the absorbance for each of these concentrations, and we plot these on a standard curve. You'll notice on the x-axis we have concentration, and on the y-axis absorbance. Don't get these the wrong way around. Put our data points in position and draw in our line of best fit. And you'll see in this case that concentration and absorbance is a linear relationship. Once you've done that, measure the absorbance of your unknown sample and use your standard curve to measure the concentration. So take the observed absorbance value for the unknown, line it up on your linear calibration curve, and bring that down to the x-axis to determine what the concentration is. Now, the law that we're using to make this calibration curve is known as the Lambert Law. In a spectrophotometer, the sample is contained in a solution cell of accurately known dimensions. It's usually 1 centimetre. The distance travelled by the radiation through the cell is called the path length. In this case, it'll be 1 centimetre, although some instruments do have cell lengths slightly shorter or longer. The absorbance is related to the concentration and the path length by the Lambert Law, where this Greek letter epsilon relates to the molar extinction coefficient, which is also known as the molar absorptivity of the dissolved compound. Most importantly, you'll notice that absorbance has a linear relationship to concentration. One important point I'd like to make here is that when absorbance values start getting quite large, and by large I mean getting towards a value of 1, this linear relationship starts to fall out. So in good practice, we like to keep our absorbance values approximately in the range of 0.1 to 0.5. If you're outside or inside this a little bit, that's okay, but it's most important to keep the absorbance of our standard solutions approximately within this range. Anyway, enough from me, and good luck in the experiment, and hopefully by the end of it you can report back on the concentration of pollutants in your water sample. Good luck.